All right, for this particular example, we are going to analyze this scenario shown in the figure here. I really like this problem because it ties together a number of different things that we've done so far this semester. It actually has two parts to it. The first part is looking at the collision that's going to happen and assuming that it's perfectly inelastic. And then the part B is assuming that that collision is perfectly elastic. So I'm going to do the parts A and B as two separate videos. So this video is going to be part A. Part B is significantly longer, so I'm going to just do that as a separate video in this section. All right, so we have the situation shown in the figure. So just talking through it real quick, we have two different blocks. They have two different masses. So I'm going to call this block A and this one block B. Block A is going to run into block B. And then for case A, which we're doing in this video, we're going to assume that that collision is perfectly inelastic. So remember, that means that after the collision, blocks A and B are going to stick together. Then those blocks are going to they're going to make or go around this loop here. And we are asked to find, so we want the blocks to go all the way around the loop. We're asked to find what the minimum value of that initial speed of block A we need so that the blocks make it all the way around the loop. Okay, so there's a lot of stuff going on here. We know that there's a collision, right? So anytime I know that there's a collision, then I know I'm going to need to do some sort of momentum analysis. So I can kind of think through that there's going to be a collision. There's also going to be after the collision. So here's maybe my two blocks together. They're going to be here and then they're going to move to this position here. So I can think about that aspect of that, the motion of the objects, or what we'll end up calling the system, is going to be, we're going to have a change in energy, right? I can think it's going to have a change in kinetic energy. So it's going to slow down as it goes up. It's going to have a change in gravitational potential energy because we have a change in that vertical position. So as I'm thinking through this problem, those are things I'm kind of thinking through of different ways that I might be able to analyze different parts of this particular problem. So the thing I'm looking for is this V right here, right? And that V is definitely going to show up in the momentum analysis that we do. So that's what I'm going to start with. So I'm going to do a before, during, after. So here's my before, during, and after diagram that we'll set up here. I spelled during wrong. So during and after. And so in the before piece, we are going to have we have our block A and we have our block B. And then during, they're going to come together. And then after, they are going to move as one. So I'm just going to call this AB. Just make one. Right, so this is my AB. So this, when we do this analysis, we're doing it right immediately before they collide and then immediately after they collide. And so A is going to have some V starting off together. They're going to have some V here. So at this part for this section, this is just one dimensional, right? I can have my my P1 plus J external equals P2 and have this in our vector form, but we can simplify that to just the x direction because for this section right here of the motion, we are just moving along that horizontal surface. So this was A and B. Okay, so in my diagram, I'm going to go ahead and put, so here's my x direction. I'm going to go ahead and label. So VA x1 is V sub m. This is that thing that we're looking for. VB x1 is 0, so it's not moving. And then after, so this V A, B, I'm just going to call this actually V2, right? And I'll go ahead and label these positions. I'm going to call this 1, and I'm going to call this 2. Okay, so I've got everything set up. I have my masses labeled, and I'll go ahead and just write here, MA is little m, MB is big M. All right, so the thing I'm looking for is this right here. So that's going to show up in my P1 term. If I have my system, so I guess I'll go ahead and identify my system as both objects. If I identify that as my system, then we can neglect any external impulse. There are no significant forces. There's a normal force of the blocks that are sitting on the surface. There's a gravitational force, but we can assume that that is insignificant relative to those forces happening between the blocks when they collide. So I have just a P1 equals P2. And so if I go ahead and just expand this out, so P AX1 plus PBX1 equals PAB X2. So my initial V for the block B, so the mass big M, that one is 0. So I'm going to go ahead and 0 that piece out here as well. So this is just MA, and then this is VA. And actually, I'm just going to go ahead and call this VM. So this is the thing we're looking for. So that initial momentum starting out is just, this one has no momentum. This one is just my mass times that V sub M. So that's my initial momentum of the system. And this is going to equal at the second part here. So my mass is A, B. So mass of A and B together. And then that velocity is going to be a V2. All right, so the thing we're looking for is, I didn't mean to cross that out there. And my pen has gotten stuck. So let me see if I can get my pen working. There we go. So this was a V sub M. So I'm going to highlight that. So this is the thing I'm looking for. I know this mass, right? And I know this mass, and I know this mass. I don't know this V. And this is the piece that's going to make this is one of those multi-step type of problems, right? So I know the masses. I'm trying to find that V sub M, but I need to do some extra work. I've got to figure out how I can express that V2 in terms of things that we know. Okay, so I did all the momentum stuff and I don't have enough information to solve. So now we want to look at, okay, what's going to happen next? So once the blocks are together, they're at this point. So we can assume that at this point at the very bottom of that circle that they're going to go through, this is still that V2, right? So this is my point 2. I'm just going to use this picture here. So this is point 2. And then it's going to go around, and we are interested in kind of the criteria that doesn't fall off at the top. So I'm going to note that top point as another point of interest. All right, so here we have a point 2 and a point 3. I already mentioned at the beginning, I know that from 2 to 3, we can do a delta E equals work other, right? We have a change in energy. I've got some kinetic energy at the bottom and the top, because we don't want the top to be 0. We want to have enough of speed so that it keeps going around the loop. And then we've got that change in gravitational potential energy. So, all right, so let's set up here what we can do here. So for 2 and 3, I'm going to go ahead and say that this is my y equals 0. So that will mean if I define some variables, I can say a y2 equals 0. This would be a v2. And this is the same v2 over here, right? Then at the top, we have a y3. And my y3 at the top, if I've got this as my y0, my y3 at the top is just going to be 2r. So it's just basically the diameter of that circle. And then we need a V3 here. So for the V3, sometimes when we're doing some sort of swing or rotating motion, we like to set that V3 equal to 0. But in this case, we're not wanting the object to stop up there. We're wanting it to keep going, right? So we're going to go to our circular motion, our circular dynamics stuff, and I'm trying to see where I'm going to do that. I think I'm going to do that over, I'm just going to use my screen over here a little bit. So if you remember when we did introduced our forces for objects that are moving in a circle, we talked about that critical speed at the top or critical velocity at the top of an object. And so if I take that point at the top, I say this is point 3. At the top, we're going to have the gravitational force acting down. And then as long as there's contact with the top, we would also have a normal force, right? Our acceleration, our A-rad, is going to be directed this way. And so we would say this is my R axis. This would be our T axis. So if we are looking for the minimum velocity is going to happen where we have that kind of threshold where we're just losing that normal force. So what we want to do is we want to solve for that velocity. So I'm going to sum of forces in the r direction is equal to mass times my a rad. And remember that is just equal to a v squared over r. So if I'm taking away that normal force, in order for this object to have enough energy, enough speed to keep going around the loop, I can say that my speed here needs to be equal to, what is our force? Our force is just the mg. So I'm going to put in mg is equal to m v squared over r. My masses are going to cancel, and my v, the v minimum at the top, this is going to tell us the speed, the slowest speed that we can go. So v squared is equal to g times r. V is equal to square root of g times r. So this is, I'm going to say this is min. So this is the minimum speed that we can have at the top and still have our object make it around. So this is what we're going to use over here for v sub 3. So this is going to be square root of g times r. All right, so I've got the V2. This is kind of what we're looking for, right? Because I need to plug this back into my momentum piece. I have a Y2, a Y3, and a V3. So I think we're in good shape to do an energy analysis. So we're going to do E2 plus work other is equal to E3. I don't have any work other. So, and anywhere along that track, of course, we would have a normal force, right? At any point, that's always going to be perpendicular to my displacement. So that's not going to do any work. And I think it said it was a frictionless track. Yeah. So frictionless track. So we're assuming there's no work along the length of that track. So that means our work other is 0. So we have just a K2 and a UG2 plus UG2 equals K3 plus UG3. And one of these is 0. So my Y2 connects to my UG2. So that guy is 0. So in here we have a 1/2, and this is the mass of both blocks together, right? Mass of AB. And so this is V2 squared is going to equal my K3 is 1/2, still mass of both blocks together. This is my V3 squared plus my mass of both blocks, G times R2R. All right, looks like we can cancel some masses here. So we're going to cancel mass. And then let's see, I've got a 1/2 and a 1/2. So I'm going to multiply by 2 throughout the whole thing. So I'm going to 2 out here and get rid of those halves. This is the piece that we're solving for, right? So I need to get an expression for that V2. So V2 squared is now equal to, here I've got just a V3 squared, and our V3 was this guy. So this is just G times R plus, here I've got a 2 times a 2 plus a 4GR. And so V2 squared is equal to, and I'll just actually solve for V2. V2 is equal to square root of 5GR. Okay, we're getting close to the end. So now we're going to take this guy. So this V2, this is the piece that we need. So we needed to take this and plug this back into here. So this V2 is expressed only in terms of things that I know, right? We know that radius, G is just a constant. And so over here, I can rearrange and say that that initial V is equal to my MAB. This is the mass, total mass. So this is little m. I'll go ahead and just plug in the values they gave us. This is little m plus our big M. And then V2 is square root of 5GR. And then on the bottom here, I'm going to divide by the mass of that little block. So this is going to be our answer, so our expression. So the minimum velocity that we need that little block to have, if it's going to hit the bigger block, we're going to have a perfectly inelastic collision, so they are going to stick together. that if we have this speed that we found, then the combined blocks will have enough speed at this point to make it all the way around that, that loop there.